Yes, I was asked for a talk from the developer's perspective. And well, I'm a compiler engineer by trade who somehow found himself implementing theorem provers, so that's about as much from my perspective as it gets. But I actually hope that it's not only interesting from that perspective, because I first held this talk at Jasmin Blanchette's group at LMU a few weeks ago, also for the metaprogramming people there that are implementing their own tactics in Lean. And of course, if you do that, then at some point you care about performance of your tactics as much as we do as the Lean developers. And yeah, let's see in which direction this goes. Maybe there's also some content for the mathematical data people who are interested, maybe interested in some aspects of this. All right, so let's see. Let's start very small. One thing you have been able to do for, I think, at least Lean 2 is just to call Lean on the command line and add -- profile. And yeah, if you do that on, say, a mathlib file, you get an output like that. Very simple. So there are some sorts of categories like importing and simp and other tactics. And whenever that gets too slow, goes above a certain threshold, a line is printed. And at the very end, whether they were printed or not, we just sum up all of these categories and print that out as a cumulative profiling report. Okay, so much yeah, for the easy part. So the first question here is, what do these numbers tell us? Because, for example, well, if we do, let's see, well, if we do elaboration, then part of that is running tactics, of course. But these numbers are actually exclusive time. So when we say elaboration, that's the parts, 1.3 seconds, that's the time not spent in any of the other categories. Because, yeah, if you add that, then quickly, then it's not clear anymore where the bottleneck could be. But that's not ideal either. So if we actually look at the numbers, for example, we see in this file, simp is by far the bottleneck, let's say. But yeah, without more structure, in the end, we're not even sure. Is someone calling simp directly here? Or maybe is ASOP, which is a search tactic, is that calling simp? Yeah, no idea. We can't tell at all from this profile. So for the longest time, this is what was available in Lean. And yeah, now we want to look at a few things to improve on that. So one nice thing about Lean is because it has as a programming language, has a relatively small runtime, you can actually just use, oh no, sorry, that is the next slide. Let's stay with the simple approach for now, because simple is great because we can actually just continuously benchmark that and record it on a website, which we have been doing since, I think, we've been doing it for Lean, we've started doing it for mathlib during the port. And yes, so if you go to that website, speed.leanlang.org, you can see all the commits in the Lean repository, in the mathlib repository, with their timings and with diffs and graphs and so on about the history. And yes, we can see there are some, okay, there are even more metrics than we saw on the previous slide. There's instructions, task clock, which is like a single CPU time, as well as wall clock, which is with parallelism, and so on. And something we added at some point for mathlib is to actually have timings for each individual file in mathlib. Which, yeah, I mean, that's 4,000 new metrics we got there, and I hope this is helpful when, yeah, I mean, doing specific PRs to mathlib, and you really want to know, well, what other files did I maybe slow down or speed up with this change? Because before, yeah, we only have the grand total, and then it's always hard to tell, especially with a project of the size of Mathlib. So you might be wondering what's up with these instructions. I said timing, but yeah, instructions is just a very convenient way to measure time because it's, let's say, relatively stable. It's not completely deterministic, but the standard deviation is maybe something like 0.1%, so it's pretty good. And so when you read numbers like this, you really should be thinking, please, I do that 10 billion instructions, that's about a second. Like that would be 10 gigahertz, which of course is a bit high. I guess we'll get there. But yeah, it's close enough.
So can you say what sort of instructions this is?
Yes, so it's in the end, it's what perfstat gives you on Linux.
Okay.
Yes.
And on like AMD 64, some reasonable server or something.
Yes, exactly. So yeah, it's very much hardware dependent. What exactly is counted here in what way and what the standard deviation is. But yeah, I think on Intel and on AMD, it's very much comparable.
It's running on the same server all the time, presumably.
Yes, exactly. Yeah. Yeah.
Is there any reason why the lean benchmarks give you a relative difference and the Mathlib 4 benchmarks seem to give you absolute difference in number of instructions?
Yes, so it's not actually a relative difference. Oh, well, no, sorry, you're right. There's a relative difference and there's a difference in standard deviation. The second one we only have for lean, because Mathlib is way too expensive to run multiple times per commit. So we have no standard, we actually do not compute any standard deviation from Mathlib. And I think for the instructions, I hard-coded in this entire software to only print out the absolute value, because in the end, I mean, you have many small files and large files in Mathlib, right? And so if you only have the relative change, that does not tell you like if one file got slower by 50%, but one file got faster, then yeah, you have no idea. Is it faster now, all in all, or not? Like, is this an important file or not? And so I assume that the absolute difference would be more interesting in this case.
If you click on the commit, you see also the change and the relative change.
Yes, then you get even more information. All right. Is there anything more to say about this? Don't think so. So, yeah, so as I said, we started doing that during the Mathlib port to Lean 4. And yeah, that I think was a good timing. That gave us data on also just how Mathlib grew. Like, yeah, really started at the beginning of last year, and then miraculously, before anyone thought it would happen, in July it was basically finished, modulo some tech debt, and yeah, we were able to profile Mathlib growing here, and also some specific optimizations we did to Lean during this time that sped things up again, and instead of just growing. If you're interested specifically in Mathlib and the performance part of that, I also had a talk on that on this slide and more at Lean Together in January. And yeah, so what we're actually looking at here is not the total times, but again split up into different components. And so when I held this talk last time at LMU, there was a big discussion about what's up with typeless inference. Should it be that way? Or is something going horribly wrong here? Okay, before we get to that, let's quickly go through some other parts which might not be as surprising. Like, yeah, of course, tactics all in all still play a big role. Yeah, interpretation is in general used by custom tactics and so on that are not compiled into Lean itself. The simplifier itself, of course,
So roughly, other tactics is other core tactics, interpretation is sort of MATLAB tactics, roughly?
Yeah, you could say so. Interpretation is a bit of a problematic metric. I've actually thought about just removing it so that it goes in the correct buckets instead, which I think would be more accurate. Yes, and kernel checking, for example, is in MATLAB at least, is relatively insignificant, only 4% of the total. And yeah, some other parts that you might expect parsing is completely irrelevant for this purpose. Okay, but let's talk about type classes a bit, just to clear some things up. So yesterday evening, I redid this chart for the remainder of last year up to today, and so type class is still at the top. That's the orange one. If we normalize everything by the task log, which is like the single core runtime, then we see that it's about 30% now. So that's already quite a bit better than 45 before. And yes, there's one big change that was I think, fun-like refactoring by Anne Banen, which was based on other changes, I think both in MATLAB and in Lean 4. That was a quite drastic improvement of type class inference all through MATLAB. So I think it's fair to say that we're still learning how to use type classes most effectively in Lean, and MATLAB is learning how to best do it on their side. And yeah, we just have to continue experimentation and improvements on both sides. Yes, but I think it's fair to say that MATLAB is just very heavily based on type classes in general, if you ever looked at the hierarchy in there. So yes, it is not surprising, I think, to anyone that type classes still are a major part in compiling Lean. Let's see, are there any other recent interesting...
It's interesting that second biggest thing now is import.
Yes, exactly. And yeah, I guess that's the light green curve that started at 5%. It was on the last slide, and now it slowly grew, which, yes, the deeper the project gets, the more there is to import in each file, which times all the files means that there is something like a quadratic growth factor here. Yes, so that will definitely be something interesting to watch in the future, and to see how we can help MATLAB grow in that respect. Yeah, I might get to some ideas on this later, because we do have ideas. We just haven't implemented them yet.
We fought against this recently in AgDev by breaking things into smaller files and being very aggressive about importing only what you need, and that number goes shh. They're like basically big files that are kitchen sink kill you.
Yes, okay. Okay, yeah. I'm not surprised to hear that we're not the first ones to have this issue. So,
and there's a long-running Zulip thread that's basically doing exactly this, like, you know, cutting up in big files and trying to split these things out. Because yeah, we do have a major issue with this kind of, you know, dependency creep in MATLAB, and so yeah.
We're getting them up better.
Yeah. But it's a philosophical thing where we've started having the library for developers and the library interface for end users, and they're different. And it's perfectly fine to have kitchen sink modules for end users, and they're happy with that, but developers should know better and not use any of them.
Yeah, that absolutely makes sense. I mean, it's also that I think for especially for beginners, if you like start a new file or just play with Mathlib, just doing import Mathlib, that's not a bad thing to do because you get all the tools without having to search for them. But of course, yeah, especially if you contribute to Mathlib, you cannot just do import Mathlib inside of Mathlib, and in fact, you should be much more specific than that. So I'm just curious, did you also think about like technical means to, for example, just reduce the work that you have to do for also transitive imports? Because that's especially something that we're thinking about.
No, transitive imports now seem relatively natural, so
Right.
mostly it's just a matter of being really obsessive, of looking at the whole dependency graph, and anything that looks weird, fix it.
Okay, nice. Yeah, so file level organization. Yeah, that makes sense.
Yeah, like about the type classes, I remember like 20 years ago in Mizar they had these like type class style mechanisms and they went a bit overboard. And what helped a lot was to look at like ATP style indexing and basically do some of these like smart indexing structures, and that really
Yes. So
brought it down to like 5–10% of these type inferences mechanism. Isn't it like sort of horn-claws style mechanisms firing like crazy all over the place? Like within.
yes, I mean, so in general, you do have something like Prolog running here in the background in Lean. One specific huge optimization in Lean 4, like this was way first in Lean 3, is a discrimination tree for quickly selecting instance candidates.
Yeah.
Does that,
That's one of the methods, definitely.
Yes, so that was a huge help, and exactly the same is true for SIMP as well, for finding, rewriting candidates.
Okay, right.
Great. Anything else that is surprising here? I think interpretation, we actually did some specific optimizations. One of them was one of my very few actual contributions to Mathlib from my side. Otherwise, yeah, quite a few are quite stable. And otherwise, I would say slow growth is inevitable in some sense.
So this profile is taken from a build, right?
From what?
From a build, from a full build.
Oh yes, this is a full build of Mathlib. Each single dot on those lines.
So now this may or may not affect what the user sees at usage time.
Yes.
So it might be different, but it's not in a build situation.
Yeah, that's true. And so specifically for Mathlib, most users just rely on the cloud cache that we host. So yeah, mostly they just have to wait for CI to do exactly this, and then they can just download it. And yes, you're right. Then if they like open a file, then for example they only have to wait for that part of the imports, and then it's a completely different question, like how fast is Lean to get to the point in your changes that you want. And yeah, so just to mention one project that one recent change that I worked on in this is to increase the incrementality features in Lean, so that if you change a tactic proof, we do not anymore have to recompile the proof up to that point, but only from your change on. So yeah, specifically like for the latency, for the performance that the user sees, I think that's a really important change. And we want to continue working on these things.
When you mentioned that slow growth is inevitable, this has already been normalized for total runtime. So actually all the growth
yes.
here is like the quadratic factors.
Yes, that's true. I mean, Well, yeah, I mean, we don't see the full task log, so it's that, yeah, it would be good to also look at the
Number on the
unnormalized.
left are not normalized, right?
Oh.
Those are the second.
Oh, yeah, sorry, you're right. The left
And
is
they're all-
unnormalized, the right is normalized so that I get the percentages.
I see.
Yes, yes. Okay, yeah, thanks for catching that. Right. Great. Any other questions about what is going on in Mathlib? Because I think we'll get more opportunities for that. Okay, so let's go back to how can we profile things in Lean, the actual topic of the talk. So yeah, I said that Lean has a small runtime, and so what we can actually do is to just use traditional profiling tools for profiling Lean programs. And yes, you get something like a stack from that. You can use, well, my favorite tool right now is this sampling profiler called Samply, which is much easier to use than anything that came before it. And yeah, so you do get some insight into this, but it's still, this might be nice if you write your own standalone Lean program, but if you write a meta program or write Lean itself, this really doesn't help you all that much because it's like a completely generic stack trace. I mean, we can see that we entered the elaborator at some point, but it's really hard to find out any specifics about that. And yeah, in the end, the mere call stack does not tell us anything about, like, for example, which theorem are we currently in. That's not visible in this call stack. So this is not that useful for profiling Lean or tactics in it. Especially if tactics are interpreted, then yeah, the call stack is completely gone. All right, so can we do better than this? Something that we had for also quite a long time is traces in Lean. So yeah, there are debug options, and if you set them, you can, for example, watch the elaborator enter a command. There's an instance here, and then it has to step through that. We get to some nested proof in there, and that's then split into singular steps and so on and so forth. We get to a unification problem. So that is usually only something that developers and, well, some tactic programmers have to look at. But I think we made it a bit more useful recently, relatively recently, because we figured out, well, what if we can simply annotate these nodes with the time it took to, well, produce that node, the time that was spent inside that node. Then even without thinking too much, what does this specific step mean? You can roughly tell, for example, oh, which tactic in my script actually took how long. It's still not perfectly readable, but I think this was a very important first step. And yeah, so let's think about how to make that more readable, because Henrik Böving at some point just wrote a small script that took exactly this output and produced a flame graph out of that, so that already helped. And then more recently, I just took that and, well, threw it in the same UI that this sampling profiler Samply did before. This is the Firefox profiler. And now we get something that has an actual tree format, and that has some queries and some transformations built into this tool. But yeah, that is at a way higher level than what we had before with this super raw call stack that did not really tell us anything. And so maybe let's just give this a try in in practice, because this is now high level enough that we can actually do this for all of Mathlib and accumulate that in a single profile. That would not be possible with a sampling profiler or anything, because it would produce way too much data. So let's see. I think I have that open somewhere. All right. So this is an entire profile of Mathlib. And yes, if I go to the root node, you can see that 22,000 seconds were spent on this. I think that's about roughly 8 hours. This is single CPU time, so yeah, this was on a, I think, 16 core, could have been this laptop. So that's much faster in practice. And there's also some profiling overhead, I should say. And maybe the first thing we can see that now we actually have not just total running times for all of these subtrees, but also self-time, like how much time was spent in this node specifically, which is information that we lacked in the super flat profile output. Okay, so what does that actually tell us? So first of all, a caveat. This timeline is great if you profile a single file. For this whole of mathlib, you can ignore that because it would still take way too much data to have the exact timeline of building all of mathlib. So this is actually, I've just summed up like equal paths in this tree. So the timings are correct, but the ordering is not, and so you should ignore this first line and focus on that tree. And yeah, so starting from the top, we have this tree that we can manipulate. We have a flam graph as well built in here. So that's always a nice visual overview. You can see that, yes, after the front end, we spend time in, what is that? In definitions, there's quite a bit of time. In itself takes some time. Instances take a bit less time than definitions. And then, of course, there's theorem. That's the big one in mathlib.
This is mostly just reflective of how many times these commands are used, right? Like in doesn't take a lot of time, it's just that there's a small proportion of ins.
Yes, okay, that is, again, inclusive time, so yes. Inclusively in the in command, we spent, what is that, 400 seconds, 460 seconds, and yeah, the self time is very small of the in command. Yeah?
So as far as I can see, this is like, for instance, the theorem is the total time spent elaborating theorems over all the theorems in mathlib. Is there a way you could also produce a profile of like specific theorems?
Yes, so there is a specific option to enable that in the export. Yeah, that's a bit of a, like one restriction of this tool. You can't really change the level of detail in one profile. But again, I think if you do that for all of mathlib, like I've done that for specific files, but if you do that for all of mathlib, I'm not sure that tool might just break. Like you might just run out of memory, even consuming the profile. And in the end, I guess, like a view like this, I think will be completely useless because like there's just so many theorems in mathlib that without some accumulation, you just don't see anything in the end. But yeah, for specific files in mathlib, that can be very useful. It's trace.profiler.output.pp if you want to have more printing per node, and so yeah, more differentiation as well. All right, what else can we see here? Well, there's our imports again at the very right. That's not a new information. And yeah, just to show a bit more what we can actually do with this graph is, yes, so now we can see an actual percentage. 44% apparently of mathlib, when I ran this, is being spent in theorems themselves. The tool already expanded the hot path in mathlib in here, but if I close that, then we also see the others. 18% definitions, yes, import again, roughly matches what we've seen before, instance, lemma, and so on and so forth. Okay, if we go down into theorem again, then we can see that, okay, yes, about half the time in the theorem is actually spent running tactics in the body. I think we'd expect at least as much. Oh, and now we see, there's actually 7% spent on running theorem again. Okay, yeah, now we get into technicalities in how Lean is implemented. If you write theorem namespace.name, that is actually unfolded into a new theorem inside a namespace. So that's how this didn't happen. And well, fortunately, we don't just have to accept that. I mentioned that there are also some transformations we can do with this tool. So we can do collapsed recursion, and now that one is gone. And now we see that all the other nodes have gotten a little more expensive in relative to the full time because that node has been eliminated. Yes. So after tactics, we do spend also some time in the header, like in the signature of the theorem, and so on and so forth. I'm not sure there's any other surprise in here. If you see something you want to know more about, let me know. Otherwise, let's see. Is there anything interesting in tactics bodies themselves? Okay, now we see some more. Lean internals, a tactic is a sequence of tactics. Okay, usually it's an indented sequence of tactics. And then, for example, there's the C dot, which we use to focus on a specific goal. So that apparently is one of the most used in time tactic inside such a block. And well, again, we can just use a transformation if we really just care about what tactics are being used in Mathlib. And for example, we don't care about the difference between theorems and definitions. Let's just focus on that function, which is the kind of nodes, all the nodes with the same label. And now we have 100% spent in tactic seek. Everything is relative to that now. And if we close that, we do see, okay, almost no one is using tactic sequences with braces in Mathlib, which is the other style that does not rely on indentation, at least by time. Like, this does not tell us anything about how often does this occur syntactically, just in time. And does that tell us anything else? Well, we have the interesting thing again that, of course, tactics are highly nested. If we do not want that, let's do this again. Okay, and now I think we get something closer to what we've seen before in the simple profile. Yes, simp is still the most expensive tactic, followed by ASOP, specifically the category theory configuration of ASOP, followed by rewrite, refine, convert. Simp A is a separate tactic that does the assumption at the end, and only then some basic ones like exact and so on. I don't think any big surprises here either. Well, but now we can actually do something and ask, for example, but what is simp actually spending its time on? Well, let's see. Type-class resolution is the first one. There's some custom dischargers, which again do type-class resolution and other things. There is unification, and I think the remaining ones are pretty much insignificant.
What's the difference between yellow and red again?
Yes, right. So so this tool uses categories to color those boxes in front of the label, and you also get a breakdown into categories on the right. And so for now, I just added 3 categories for Lean, which are elab, meta, and other. Like if I go back up here, we see that in all the tactics we spend 45% in elab, 43% in meta, and 12% in other. Okay, so what is the exact difference here? Elaboration is what we think of the surface level, like the specific implementation of a tactic, and meta is the plumbing in some sense, like, yeah, just general algorithms, procedures like unification and type class inference. So yeah, that is just a categorization that exists in the Lean source code, and so I've at least exported it here to give it some differentiation. Yeah, I would be interested in what other categories we could add here, but I guess these are the main ones. And other, for example, kernel importing, something like that, that really does not belong to either of them is currently categorized there.
So red means this thing is ELAB heavy.
Yes.
Okay.
Yes. So red at the node specifically just means this node has been categorized as ELAB.
Okay.
Yeah. Sub nodes might be categorized differently. And then if you click on a node and look at the right-hand side, you can see the total breakdown inside the subtree. And yes, so it would be interesting actually what's otherwise going on in that tree. I'm not totally sure if I can do this with this UI. So we can't, for example, focus on a category. That can be helpful. And well, we have at least one gray node here, so maybe let's just try that. Okay. Now we see, well, ASOP is a tool that's not in Lean core, and so it uses its own trace classes, and yeah, it did not decide to start those classes with ELAB, so it's categorized under other, currently at least. Yes. Okay, so we do spend some time in this function. That also is a custom tactic that looks like, Nomcast is a custom tactic. So, okay, so you could say this is maybe something like a miscategorization, just resulting from the specific implementation of the user tactics.
Is all of the kernel represented here, or like?
Well, we are currently inside the tactic profile, so we would not expect all that much, if at all, kerneled, right?
But I mean, from the start,
yes.
Would all of the kernel runtime be represented in?
It should be in here, yeah. Like if we close that down, or where is that? We can also just search for it. And I'm always confused how to actually find it, because I think it's not immediately, yes, it's not expanded, but at least if you expand some things, you can find it. Okay, so in theorems, okay, now this is relative to my current search. Okay, yes, if in theorems apparently 1.1% of the total runtime is spent in the kernel in theorems. And now you could do some transformations again, like focus on that if you want to know it more specifically across definitions and theorems and so on.
And so there's a trace message that's happening for the kernel?
Yes.
Okay.
Yeah, it's just called kernel. And there's no further information right now because that part is implemented in C++. But yeah, the Lean part just sticks that around the C++ call.
And then if there wasn't a trace class, then it would just be blamed on the parent node, I guess?
Yes. So that is a restriction, a caveat you should keep in mind when looking at these profiles. One other caveat, just to mention it, is I may have mentioned that there is a threshold above which we do activate these nodes and count them. So if anything that is below the threshold is not represented here. So yeah, if you see a self time at a specific node, that could be really time spent in that specific elaborator, for example, the app elaborator. It could also be time, insignificant time spent in any of these children. which of course in some could be significant, but that would be very expensive to profile accurately. So that's a current limitation of that too. Okay, I think I should go back to my slides to make some progress there.
Oh, could I just, like Larry Paulson had last year during some lean talk at ITP, this very funny remark, how can definitions be expensive? And could you elaborate?
Yeah, so without, as I said, we don't see which definitions specifically are expensive here. And I mean, just thinking, for example, about category theory, where everything is happening in definitions. Well, most areas, like, there's a lot happening in definitions, and they can also contain nested proofs, of course. And yeah, so then you quickly end up with a lot of time spent in definitions. I mean, in general, in dependent type theory, you don't really have built-in distinctions between definitions and theorems.
Yeah.
It's something Lee added to say, well, usually we want propositions in theorems, but yeah, it's not actually stopping you from putting them in definitions, and especially inside definitions as well.
And I guess also the fact that you sort of count tactics as elaboration would be sort of unnatural to the Isabel people, right? Like it's sort of.
So for them, tactics is a completely tactic execution would be a completely separate step from the.
I mean, type inference in Isabel is sort of, well, okay, so you do have some type classes, right? And it may cost you a bit, but in general, I think this is all reasonably cheap, and that the tactics are doing the search, whereas here it's sort of more elaboration style search.
Yes, because you can switch between term mode and tactic mode anytime in the, yes, there is no distinction. Tactic evaluation is a part of elaboration. All right, great. So let me tell you about some other tools before we stare only at this graph. So that's basically what I showed. Okay, yes, there's actually only one more tool that I wanted to mention, which is even newer, and it's the option diagnostics. So it has a very general name, and we want to have it. We wanted to have a very general purpose. Basically, whenever something is unexpectedly slow, we hope that diagnostics will give you some interesting output, helpful even, and we want to improve and add many more features in the future. So, okay, what's going on here? What does it do today? So it mostly counts, for example, what did unification have to unfold, what declarations and how often, what instances had to be unfolded. There is also a separate, it's not on here, but what instances were used, were tried to apply during typeless synthesis. And we also have a separate counter for what SIM theorems were applied. And so I don't have a specific example for how to apply this, but just as a general guideline, I would say, yes, if you have a slow definitional equality, a simp call, typeless inference, this tells you much at a glance what is happening in this tree, in this call tree that's happening behind the scenes without having to look at some structural tree, and especially if you see any name in here that's like high up with a high number that you did not expect at all, that's always a very good starting point in optimization. So, for example, if you see a SIM theorem that should not be there, maybe it's just a bad SIM theorem, maybe it just applies to too much. I think we've had multiple PRs to Mathlib now that just found bad SIM theorems using this tool, and sped up linting in Mathlib by 17% or something. Yeah, if you see a completely unexpected instance, maybe that should not be a global instance, maybe it should be scoped. And yes, if you see a declaration that has been unfolded and you think, wow, there's no way this unfolding this helps, yes, we do now have new tools to mark definitions irreducible to the system in a scope, which is the new seal command, and unseal as well. That I think should be in the 4.10, which is now at release candidate 1 release notes if they are updated.
So these stats here, what did they scope over?
Oh, yes.
Why the bleep nat.rec 100,000 times? What are you doing?
Yes, so unfortunately I'm not quite sure anymore. What was the specific example I took here?
But it's generally one declaration, right?
Sir?
It's one declaration.
Yes, yes, I mean,
100,000 times.
yeah.
Computing.
Sure, probably in unary. But why?
No. I very much doubt that that's computing in unary 100,000 times. I think that is 100,000 separate applications of during like a type class search or something. I agree with your point that like that is a very suspicious thing and we should look up why is that happening because that is,
Yeah, I should have recorded what the specific example was that led to this.
I mean, it's probably something about positive compacts.
Yeah,
Yeah.
it's very should narrow it down quite a bit, but
Yes. Yeah, so I did look at it. I did look at it in the editor as well at that point. And unfortunately, I did not immediately say, oh yeah, this entire subtree is completely garbage. We should just skip that by removing something, some instance, some reducible definition, and so on. Yeah, unfortunately, it's not always easy just by seeing high numbers to remove them. Okay. Yeah, that is about everything I had to say to profiling. There's still a bit of time left. Are there any questions?
Well, yes, so I would be interested to know what the type class part does in particular.
You mean where it spends its time on?
Yeah, so can you say a bit more about what kind of processes are involved?
Right. So, yeah. So at a very rough, like top-down, type class search is a backtracking search. Like we have overlapping instances, especially transitive instances. Like if you have this mathematical object, you get this one for free, and that's like coming from 10 different directions at the same time. Yeah, and of course, any application, potential application of such an instance has to do unification. Yes. So that's like, I think the big process that takes up time inside of type class inference. And then it turns out that unification itself actually has to call use type class inference in some places, so you actually have a mutual recursion between these components. And yeah, that in itself, of course, makes it hard to basically see, oh, is it type class inference or is it definition equality that's the culprit here? Because yeah, you just get a really deep nesting between these. Yeah, I would say that's the parts that in the end make type class inference as expensive as we saw. It's a huge search tree, it's a backtracking search tree, and at each node, well, fortunately, we first use the discrimination tree that helps with trimming down the set of candidates, but then for each remaining candidate, yes, unification is definitely one expensive step when you repeat it everywhere in the graph, in the tree. And well, it's a graph with our inference algorithm that avoids common subproblems. That was one additional optimization in Lean 4, but yeah, that I would say that other.
Sorry, what did you say?
So in Lean 4 we use a table resolution algorithm that avoids resolving common subproblems in the type class inference.
I mean, the question, the underlying question is, do you see, the fact that, of course, there will be more and more mathematics involved, and so, do you see that part in particular as a possible, limitation at some point, or we need to rethink about the algorithm so that it can, more mathematics can be put on. And also another question is because we were speaking about like optimization techniques in machine learning. So do you feel like there is some possible description? I mean, it's two questions. Okay. The second one is possible description of the parameters. The space of parameters on which you could then try to optimize. Using learning. I mean, that's the second question.
Yeah.
Sorry,
Yeah, no, those are really good questions. I have not, we haven't thought about ML applications in this area specifically. I would say I've seen papers, for example, doing applying ML to compilation in like traditional compilers. So I think this definitely is a direction of research. And yeah, I could see like it would be a worthwhile research direction, let's say. But yeah, no specific plans so far. And yeah, to your other question on yeah, how could this evolve? Could that become an issue at some point? Yeah, I think as we saw in the graphs at the beginning, I think like it was at 45%. Now we have it better under control than before, I would say, and it's not like growing rapidly again. So yes, really, I think we just have to work together both from the library side and creating reasonable hierarchies of type classes. And yeah, I think Mathlib people are constantly reevaluating how exactly these hierarchies should look like, right? But also, of course, from the Lean side, there could be specific changes we could make to speed that up or to make it possible to do refactorings in Mathlib that would then help.
I wanted to give another response.
What are you trying to optimize?
Sorry?
What are you trying to optimize? What are you trying to get from the profile?
Oh, okay.
Optimize our...
So this one specifically, the trace output, I actually wrote that for the incrementality project to get a sense of where Mathlib time is spent in Mathlib in the large. So, for example, I wanted to make sure that we do spend most of the time in theorems, which was true. But yeah, so since incrementality was specific to theorems, I really wanted to make sure that I'm optimizing the right thing. So that's the specific reason why I wrote that tool at that point. Yeah, and I do hope that this will be helpful.
Some of these things may or may not be bottlenecks. Some of them might be things where you're seeing a certain growth rate or slowdown rate, things like that. So I'm curious what kinds of things like that you're seeing that then inform what you're trying to optimize.
Yes. Yeah, that's a very general question that I'm not sure has a general answer. Yeah, we'll just have to keep looking at these metrics, and specifically those graphs are just very good at finding regressions as well, especially unintended regressions. Yes, so we have plans for example, we see import is growing, we have plans to attack that. Yes, I think that's that's some of the things in my head right now that I can add there.
Yeah.
Just replying?
So I wanted to remark on your question about like, oh, does higher level mathematics mean that, you know, this is gonna keep growing and, you know, we're gonna have to worry about it? I think that at a sort of very abstract level, you can argue that like, actually, no, this shouldn't happen, that like, you know, math is a large graph, but its out degree is bounded by human ability to understand things. And so, you know, no matter where you are, you can always draw a neighborhood of a certain size and then do your proof there. And so these are all sort of like technical issues that arise as a result of all of the ways in which we're not O1, right? Yeah. But like, those things can be addressed, you know, you can have like module system, you didn't mention, but like module system can be used in order to say, oh yeah, all that other stuff, it doesn't matter. It's just, it's not gonna be imported or loaded in any way. And then then the problem becomes O1 again, right?
That is important.
Yeah, yeah.
So I would like to drill in on this. Think of indeed math as a graph. The important factors are kind of the dependency depth, which is something that's going to matter. Just having more at the same depth level is probably not going to hurt super linearly.
Right? Having depth is okay. Like as long as you don't unfold all of those layers of the stack, you don't need to know how much more there is to.
But that is kind of frivolous depth, whereas conceptual real depth is I think that we can't escape.
No, I mean like you can build the real numbers, and then you can build on top of the real numbers, and then when you're working about things on the real numbers, you never have to ask the question like, how were the real numbers built? It does not arise in the proof. It shouldn't be a thing that slows down your brain or Lean's brain or anyone's brain thinking about that construction. And then similarly, if you start layering construction on top of each other, building deeper and deeper concepts with more, you know, because they're defined in terms of, I mean, this is how abstraction works, right?
But this is just definition unfolding, which would be insane. Like if you were unfolding everything in a large library, I think nobody's doing it. But like, it seems to me that with type classes or with all these hierarchies, it's sort of a different issue.
No, yeah, exactly. Type classes are an instance, they're not O1, right? They are actually going through the whole, and that's something we're gonna have to address at some point, right? Like, like these designs don't necessarily scale, and we might have to think about how to improve them. And I mean, that's what a lot of this, you know, profiling things is determining like, okay, at what point is this the best solution, and at what point are alternative solutions better and worthwhile, and so on.
Right. So dependent type theory, by its very nature, really likes doing delta expansion. Yeah. Really likes to do that, and that kills you.
But I mean, for instance, you mentioned natural numbers, but sorry, but for instance, if you look at different definitions of the reals, yes, you want to have some form of parametricity. I mean, so it's not about this, but the way things are defined, sometimes, I mean, we would like to be transparent. Thanks, anyway.
So yeah, maybe just to in one sentence summarize one way we want to address many of these common issues is, yes, how can we make Lean libraries more modular? How can we make sure that we only depend on the things we want in a file? How can we, this entire context, how can we minimize that so that we does not have to search in so many directions all at once?
Mm-hmm. So you turned from a compiler person who tries to make the compiler better into an interface person that tries to give your clients enough information for writing better code, right?
Yes, yes.
Okay. Are you sure those are different concepts?
Classically, in my age, yes.
Pushing some tetrapod direction.
Okay, there's cake.
Yeah.